All right. So we left off at elastic net regression. Okay, next is Poisson distribution, Poisson regression. Now Poisson regression, even before going to Poisson regression, we have to understand what Poisson distribution is, right? This we learned it in statistics class. So basically Poisson distribution talks about occurrence of events at a given time rate. Something like if you're working in a call center, number of calls that may come from morning to evening to night. So that rate, that will have its own rate, right? In the morning the average rate would be so many calls may come, in the afternoon so many calls may come, in the evening. Okay, so that way Poisson distribution talks about something that has this time frame. Okay, it looks like this. So initially okay, let's look at something much simpler graph. Yeah, so Poisson distribution, let's look at one example. For example, calls per hour at a call center. So let's just say in the morning the rate of calls is too low. Okay, then it starts to pick up. Okay, up until it reaches at a certain point. Okay, suppose 10 calls are received per hour, then we can calculate the Poisson calculator, right? I mean Poisson distribution we can calculate. It looks something like this. So if you go and see the images, it looks something like this. First it will be low, then it will increase, it will peak, and then it will reduce. Okay, number of calls also depends on the rate, lambda. Okay, rate, average rate at which the calls are coming in. Another example is how many people are walking into a restaurant. See, nobody will go to restaurant early in the morning like 6 a.m., right? If you are going to go to a nice restaurant to have some meals, nobody will go at 5 a.m., 6 a.m. People start to come in after like let's just say 7 a.m. 7 a.m. slowly it will increase. At peak hour would be 9 a.m., 10 a.m. Some people will have 11 a.m. also. After that it will reduce again. Then again it will increase at 1 p.m. 1 p.m. to 3 p.m. it will increase. Then it will fall down again, the rate of people walking into a hotel. So those things will represent Poisson distribution. Poisson distribution is where starting there would be a pickup of the rate and then it will fall down. Okay, so in such cases, okay, we have Poisson regression. Now you have to understand, even before I talk about this, you have to understand one thing. What are you trying to predict in each of the cases? See, in linear regression, your outcome target variable that you're trying to predict will be a decimal, will be a float value. Okay, it would be something like 5.6, okay, or 11.9, or something of that sort. Okay, some float value. Lasso regression also is the same. Okay, ridge regression is also the same. Elastic net also is the same, because there are slight variations to just the penalty is added, but the ultimate prediction float value, target value will look the same only for all these three, for all these four. Okay, logistic regression on the other hand is not like that. What logistic regression is doing is, it is taking these numbers and converting them into something called as logits, probabilities. Okay, it is giving you whether a animal is cat or dog. String values, basically. String values is what you are getting in logistic regression. Okay, whether it is a cat or dog, or whether a person is going to default the loan or not, yes or no kind of answer are being predicted in logistic regression. Poisson distribution is not like that. Poisson regression, what is it trying to predict? It's trying to predict counts. Okay, integer values like 4, 3, 1. Okay, although due to matrix multiplication you may get float values, but we'll have to answer the business question in terms of integer only for Poisson regression. Okay, this difference you have to be aware of. So that is what Poisson regression is used to model count data and contingency tables. Okay, contingency tables means frequency tables. So count data should be your target variable. So your dependent variable, target variable, y, we are talking about y variable here. It should follow a Poisson distribution. That means it should increase with certain time and it should decrease. Okay. So that is when you can use Poisson regression. Mainly it should be a count data, something that occurs with a period of time. For example, number of car accidents per week, number of customers visiting a store per day. If you want to predict such things, okay, you have to use Poisson regression, not linear regression. Okay. And another case where you can use Poisson is event rate data. You should have the average rate, for example, number of infections per 100 person, okay, 100 people over a certain period of years. So such things can be measured using, predicted using Poisson regression. Again, non-negative incomes. Okay, so this also can be done. For example, one example is given here. A university is trying to predict, okay, is trying to examine how many students are who graduate from specific program are going to get better GPA. Okay, so in that case, your target variable looks like this: your entrance exam score versus how many scholarships they are going to get basis on the score. If their score lies from 60 to 80, they are not going to get the scholarship. If the score lies, again, depends on some, you imagine like this, there is a factor of reservation, caste system also, right? So based on that, if the scores start from somewhere around 68 to 92 somewhere, they'll get one scholarship, or for two scholarships they have to be very good, 80 to 90 plus, and again like this, the scores you can understand. So in these cases, look at the data points, how they are distributed. All the data points are in one line here, one line here, one line here, one line, one line. So in these, if you observe your target variable to be of this nature, that is when you can go ahead and use Poisson regression. Okay. Now, another example, good example is policy holders. So how many insurance claims a person might file if he has already filed, if he already has a prior claims, or how many years of insurance he has, or what is his age. Basically done. Basis on this, you can use the Poisson regression. Now there are two ways to use Poisson regression: either using the old way, which used to be a stats model way, where we used to write the formula directly, and accordingly, I mean for this formula we used to directly implement the Poisson. Okay, this is the old method. You need not use this method, but I'm just saying this, such a method also exists. When you implement this, okay, this was a statistical way of doing things. Okay, so and when you call a summary, you can predict as well. Okay, predictions you can get, and when you call a summary, you can see 1.316 is the predicted value, but here's the thing, like I said, matrix multiplication will yield some float value, but you'll have to seal. If you want to in a business terms, if you want to explain this, you have to explain, sir, I mean, how I would explain this. First line is people of average age of 25 years who have 1 year's who have insured last year. Okay, there is a chance of them filing two claims. I'm kind of either making it as 2 or making it as 1. Okay, they may file one additional claim on top of 2 claims. Okay, this is how I would talk in terms of business. I can't say 1.377. Okay, I have to either make it seal value or floor value. Okay, especially for Poisson regression. Poisson regression, if you're going to talk, this is how you have to explain the results. Again, there are a lot of metrics generated. Intercepts are nothing but the C value. That is the error rate, how much error exists. This is all the error the model has made. At 25th percentile, or you call it as 1 standard deviation. If you see these values: 1 standard deviation, 3 standard deviation, right? No, actually 3 standard deviation plus 3 standard deviation. If you see, this much is the error rate that is coming out, this one you can say. And coefficients are fine, standard deviation error you can talk about. On an average, how much variation in errors is being calculated by the model away from the mean. If the mean of all these years turns out to be some 2 value, so model is additionally adding 1.77 to that 2. Okay, so that much error, this error is kind of has to be reduced. And age also you can see 0.233, this is good. And prior claims. Okay, so this way you can understand. But the newer way of doing it is your sklearn library that you use. You can directly call the Poisson regression. I have taken the same data frame, claims I'm trying to predict. Okay, and you can calculate the mean absolute error, mean squared error. This is really good. On an average, the model has made only 2.25 claims of error. Okay, and I have taken the seal value of the predicted value. Predicted value was somewhere around 1.5 something. So the actual value is 2. Okay, here it predicted using the old method, it predicted the value is 1.31. Here using the new, it predicted on the same data again, it predicted 1.49. Okay, so that you have to be aware of. So go with the new way of implementation. So when you talk about this prediction value, this is how you should explain. So on an average, a person with certain age would have, there is a likelihood that he would file 2 additional claims in future, okay, on top of existing ones. So these are predicted claims, right? Future claims. So that is what you can talk about. Okay, understood? Poisson regression.
Yes.
Okay, so just remember when to use it. That should take care of it. Rest you can, code wise you can get help on code. Anyway, next is quantiles. Quantile we already know what quantiles are. We have calculated these in the box plot: 25th percentile, 75th percentile. So what happens is, this quantile regression is used to estimate how much, if I want to know, let's just say I want to know how much, whether a person will become will have cancer or not. Okay, let's just say a very simple example. For that, I will say what stage of cancer he will get. Okay, now on top of that result, I also want to know what is my confidence interval. Okay, for this particular person, whether my model is predicting whatever the value that my model has predicted, is it lying within the accepted range of 25th to 75th percentile, or usually 0 to 95th percentile. It should not be like you are trying to predict if a person is or what type of what stage of cancer he has, and it should come out like outlier. It should be far away from the percentile. It should not be like that. Okay, your prediction should make sense. So to ensure that, we also calculate the quantiles. Okay, so basically we say whatever you have estimated, how far away is it from the mean, that quantiles you give me. Okay, whether it is 25th percentile, 75th percentile, 95th percentile, whatever, it depends on the business use case. Okay, so whatever they ask you, you can put that value, or you can suggest that value for that. So in such cases, we use quantile regression. If the ask turns out to be a quantile, then you can use this. Okay. Next, if you have usually this is calculated, quantile regression we use if you have non-normal distributions. Nothing but, let's just say you had non-normal distribution, you transformed it. That is a mandatory step in linear regression. You are transforming it, but upon transforming also it is not coming out to be a normal distribution. Then what do? You can go with quantile regression. So when your data doesn't meet the assumptions of normality or homoscedasticity, this we have learned right in previous class, homoscedasticity, heteroscedasticity. So when that is the case, you have to use quantile and again homoscedasticity and robustness. Robustness means outlier impact. If there is too much of outlier impact, then also or if there is any skewness, you can go ahead and use the quantile regression. One example is, suppose you have a data set where the test scores from the students are there along with the hours of study, and you want to understand how much of impact would a number of hours have on their studies or on their test scores. In that case, what you want is not just the direct value, not a single value. Okay, you also want to know the percentiles. So in that case, again you can use the old way of doing things. So you can calculate the formula. You have to write it yourself and then feed the formula here. Okay, this is old way of doing. You need not remember the formula and all of that. Okay, so but you can still, as you can see, you can take the quantiles for which you want to calculate. You can take the data and put the data along with the inside the function that you have called, and you should be able to get the such results. Okay, now from this there is too much of explanation here, but I will only explain the important ones. So let's just say all these results are three different results. You can see from here to here is one result for quantile 25 that you see here, and from here to here are another result, another set of results with different quantiles, another set of results. Okay, and ultimately you are given the median value, midmost value. Okay, so for 25th quantile, as you can see, you have only intercept and study hours. So basically what the model is saying is 93.77% of R squared is obtained. That means the model has captured all that 93.77% of variance for 25th percentile range, wherein which the model is saying on an average, if a person studied for 3.2857 hours, he would, model is 93.77% confident that he would fall under 25th percentile bucket. Okay, that is how you read it. Next is 94.06% of the time the model is saying that model is successfully able to capture 94.6% of variance. Okay, for people who have studied 3.25 hours and they are falling under 50 percentile bucket. Okay, additional, okay, this has to be additional, I suppose. And on top of that, 3.20 is additional value. Again, the model is high variance is being captured by the model. That means the model is very sure, okay, that a person who initially studied for 3.28 hours, he would fall under 25th percentile. Again, on top of that, if a person studies for 3.2 hours, he would fall under 3.25 would fall under 50 percentile. Again, 3.2 would fall under 70. And that bifurcation is done here. That median is predicted here. Okay, so all these results are explained at quantile level. Now the model is explaining at hour level, study hours. So if a person studied for 1 hour, there is a likelihood that his test score, okay, here it is. So his test score was 55, but the model thinks that on an average, the middlemost value in that distribution is lying at 55.74. That means not exactly the average, but the middle value. So model is saying that it is likely that this person is closest to the middlemost value in the distribution who studied for 1 hour only. A person who studied for 10 hours, that value is already at the middlemost value. Okay, these are not averages, these are predicted medians for some reason. This is like I said, this is the old implementation. This is how things used to be, and we would also compare the residuals, errors. Error rate is, here is 8, here also it is 8 only. Okay, there also 8 only. Anyway, but this is how it used to be. If you have the vertical values, see the number of, here they are showing number of cylinders, you understand it like number of hours of study. So if a person studied for number of hours for 2 hours, here 4 hours, here 6 hours, okay, 5, 6, 8, okay, his scores would increase higher, okay, and the percentiles are calculated. For 10th percentile, you can see the values are low, lowest values exhibiting the same behavior. 90th percentile means the highest values exhibiting the percentile. Anything outside the percentile range is kind of a outlier, okay, so they don't exhibit the normality. That is what it means. And the actual OLS model means linear regression. Linear regression model, if you plot a line, it would fit like of this black line, okay, it would fit somewhere here, but there are additional data points which also show normality, which fall under this 90th percentile, which are these, and anything beyond this 90th percentile and 10th percentile range is kind of an outlier. That is what we understand from here. So you can implement the new way of doing this using.
Can we say here? So can we say that the this quantile regression is used for? Can we use it for the bucketing?
Yeah. I mean, yeah, correct. So if your target variable is exhibiting a behavior where you want to predict such counts, okay, it's not exactly bucketing, because bucketing would mean there won't be discrete values, but they would be discrete values, but they would be on a histogram, they would be covered next to each other. They won't not exactly bucketing, okay, you understand it like that. It's just that if you want to predict a value, certain value, and you want to show that what is the normalcy. Okay, let me give a different example, much simpler example. If I say what is classified as distinction, okay, usually 85% and above is classified as distinction, correct? Do you agree? But there are people who also secure 95%, right? 95%, 99% also, right? So now the question is, how do you predict if a person is going to secure distinction or not? Well, let's just say that's the problem. Predicting what is the percentage of values. Your model predicted, okay, someone is at 85%, someone is at 85%, someone is at 95%, someone is 90, and all of that, okay, this category predicted. And there is another category wherein which the model is saying, okay, some people have 75 to 60%, which are falling as first class, and another person are 60 to second class to up to 50%, and some people are getting first class. Okay, now in order to predict where the person is falling, you have to talk about quantile regression. Why? I'll tell you. If you want to predict if a person is FCD or not, that means what are you predicting? You are predicting this entire range, 85 to 99.99. You are predicting, assuming no one will get 100. Okay, this is what you are predicting. This is your lower value, this is your higher value. Now the lower value somewhere here to be classified as distinction, this point, data point, lowest data point would be 85%, 85.0 to be exact, and this point would be 99.99%. okay, highest data point. Now what you are saying is, if you fit a regression line, it will come like this. Assume it to be a straight line, somewhere like this. Okay,
Yeah.
but you can't, if you predict, what is this best fit line telling you? Somewhere around some, let's just say 90%. But you can't say 90% is the FCD, no? You have to consider the lower value of this range as well as the upper value of this range. Do you agree? Even though you're fitting a straight line there, straight line will predict somewhere around 90, but you have to also predict what is the lower range of that particular value to be called as FCD or distinction, and the upper value to be called as distinction. So this entire range will become quantile. This would be, you would say, let's just say if I'm to go with 10% quantile and 90% quantile, I'm saying 10% of the values present in that FCD range are captured by the model, which turn out to be at the 85th percentile. 99% or the 90th percentile of the values, or 90%, or in other words, how do you put it, is 90% of the variance is captured by the model, which turn out to be at the 99th percentile. Okay, that way you define the quantiles. Basically, range, if you want to talk about a range, certain range, the likelihood of your point falling under certain range, then you use quantile. Okay, and this is applicable only for certain unique type of problems only. Okay, where you want to calculate the some discrete values with certain ranges. Is that clear? See, bucketing is different. This is not exactly bucketing, because if you look at this example in the graph, you can't bucket number of cylinders. They are exact values.
Yeah.
Okay. All right. And last two more types of regressions we'll quickly cover and finish it off. Next is stepwise regression. Now, stepwise regression is a variation in linear regression only. Okay. Here we do things differently. That's all. That is what the difference is. This will still fit a linear regression model, same as linear regression what we saw, like lasso, like ridge, like elastic. Stepwise is also very similar, wherein which is going to fit a straight line, but the way it fits the straight line is different. What it does is, it has something called forward selection and backward elimination, or bidirectional elimination, wherein which it will first take one single feature, okay, try to compare it with predict the target variable. First it starts with no variables, then keeps on adding one variable at a time until, so the moment it starts with the first variable will capture certain variance and will be able to explain the model to certain little bit, okay, and again it will add the second variable, some more variance is captured, and those results are able to be explained and predicted as well. Okay, until this process is repeated until no further improvement is made or no further decrease in the loss function can be done. Okay, so up until that point it starts doing that. It keeps taking one feature at a time, keeps improving the accuracy, keeps decreasing the error rate and all of that. And it does this in backward elimination also. First it starts with all the variables, then it keeps on removing one variable at a time until you can't make the model worse anymore. Okay, you cannot make the decrease the accuracy basically. Okay, next is bidirectional is a combination of both. Okay, and this stepwise is used when you have large set of variables. For example, just to predict the next video you will watch on YouTube, what YouTube does is it uses immense kind of 100 plus different features. You can read all about it. They have figured it out how YouTube does it. There is an entire different video as well as a blog posted on that. So there they use huge number of variables to predict what you're going to watch next, or what should be displayed on your feed next. So in that cases, you want to understand how you can't, first of all, you are in a scenario where you can't remove the features. two, you are in a scenario where there are huge number of features. You can't further eliminate. In that case, what you will do is you will keep on using one by one and understand which is contributing the most important factor, which is the most impacted predictor variable, and in that scenario you can use stepwise regression. Okay, and this also helps in getting you the good fit model. Okay, so in those scenarios we can use stepwise regression. For us, mathematically also we'll see, but just for now, so if you wanna understand how to implement, I have taken a diabetes data set, wherein which there are certain columns like age, sex, BMI, BP, and a few other medical columns, and basis on this we want to predict if a person is going to be diabetic or not. That is our target. Now how you would do is stepwise regression using forward selection. As you can see, you have to write a initial feature, you have to write a custom function. This used to be the old method, by the way. Okay, so using the stats model. Okay, this used to be the old method. So you would write a forward selection method wherein which you will provide x values and y value, and you will provide a significance value, p value. Basis on nothing but at each iteration you're trying to calculate a test. You're performing a test whether the sample data that you have taken is coming closer to the explaining the y values. Okay, it could be f test, it could be t test, whatever the test you do. Okay, basis on that, if your null hypothesis, you fail to reject your null hypothesis, you keep the feature. That means the feature is important. Otherwise you remove the feature, then you make a copy and you apply the same thing to rest of the features. This entire process is repeated over, I mean the OLS is calculated for rest of the features, because this is in while function, no? So this is repeated for all those features, and p values are sorted, and wherever it is p value, whatever the calculated p value is less than the 0.05, you just either append it or remove it basis on that. Okay, basically if it's lesser, that means it's a good feature. If it's more, then there is not much impact of that feature on the model. Okay, your alternate hypothesis says the impact of feature on the model is not significant. Okay, if it's lesser, it's significant. Higher, it's not significant. Hence you are going to remove that feature. Okay, so this way you will do the forward selection and final model will give you the entire result. So as you can see here, okay, BMI and all of these things are calculated, coefficients are calculated, standard deviation error is calculated, and lot many things are there. See, Durbin, Watson, Jarpa, Bera, so JB. So these were used to be the tests. Okay, so that we calculated, that we would calculate, basis on which we would select the features. Ultimately you would get a model where it would finally give you these are the best models, best features that are predicting. Rest of them are not good, hence eliminated. Okay, so that is how. So in this case F test has been done. Okay, F statistic you can understand, and your R squared is very poor. This model has not done good job. Okay, only 51.5% of variance is explained. This is how the stepwise regression would work generally. Okay, forward this thing. Is this clear?
Yes.
Okay, all right. Now the next thing is most important, highly used model. The last one, I will cover this and stop. So the most important new method, most used for linear regression kind of problems is Huber regression. Okay, it's a variation of linear regression. What it does is it makes only slight changes to your cost function or the loss function that you calculate. First of all, let's understand what it does. It introduces the simplest method. We call it as ordinary least squares. Nothing but the distance between the points and the best fit line, the squares of that has to be calculated. Hence we call it ordinary, because there is nothing fancy there. Least squares, nothing but the least distance squared has to be calculated. Okay, so this Huber regression, it calculates this as this along with a variation of this. Okay, that I will explain. So this has to be used when outliers are present. Mainly if your outliers are huge, you are going to use Huber regression. Okay, and Huber regression is not very sensitive, and it's also not very aggressive like quantile regression. Quantile regression is very aggressive to outliers. Irrespective of outliers, it will try to get you the best results. Okay, but if you want to hit the sweet spot, so you can use the Huber regression. Next is if you have a chance of data contamination, very big problem. I think we have not covered this, so I will talk about this in next class. Data contamination is a big problem when you're doing a modeling, okay, machine learning modeling. So in that cases, if you think there is a chance of data contamination, then also you can use Huber regression. Basically very simple. How it works is, although you're seeing this fancy kind of symbols, don't worry about it. All it says is, when you are calculating this y minus y cap, if it is below certain level, what level that we will discuss, if it is below certain value, certain range, then what you do is you calculate the mean squared error, the same way how you do it for linear regression, normal linear regression. If y minus y cap is below certain level, you do the normal linear regression. Or if your y minus y cap, that means your loss or the error rate or the residuals are too high, very high, then you make slight modification in that. That is, you're going to subtract half of that rate from the whatever multiplied by whatever the rate is. Nothing but you are adding the quadratic term for small errors. Okay, if y minus y cap is greater than delta, so you're going to add a quadratic term, nothing but it will treat small residuals like ordinary squares. Okay, and for residuals with huge difference, it will treat like a linear loss. Okay, quadratic loss for small errors, linear term for large errors. In other words, in much simpler words, it's like this. If your error rate is less, okay, then you go ahead with calculate the same mean squared error ratio, no change there. If your error rate is too high, then you additionally multiply that with a delta value and then subtract with half of delta square and then decrease that error rate. Okay, so that's what you're trying to do. That is the variation. Loss function variation. There are two different conditions now. Okay, condition 1 and condition 2. That is what the difference is. Okay, in other words, see the blue line. This blue line is what linear regression does. Why it is doing in this direction is because of these outliers. These outliers have shifted the line, this linear regression line, towards in this direction. Okay, ideally it is supposed to be in the direction of this green line, but due to these outliers it has tilted little bit, tilted across its on its central axis, so it has come down like this. Okay, but what Huber regression will do is it will ignore these outliers. Okay, it will only take the main data points and calculate. Wherever outliers were there, it increased the penalty so that these points would become negligent. Okay, negligible impact would be there, and hence you can see Huber regression is this orange line. Okay, very recently they came up with another regressor called ransack regressor and Thielsen regressor. These are again slight variations of linear regression. So they also are best fit lines. They can work better in terms of outliers. Okay, is this clear? What linear Huber regressor is doing to the penalty term? Basically, it's also adding penalty, different penalty. That's all.
Yes.
Yeah.
Okay, and if you want to implement it, you can directly import it from sklearn Huber regressor. Okay, here I have imported two things, Huber regressor as well as ridge, because ridge also helps in treating outliers to certain extent. Okay, so Huber regressor, I have taken 500 samples, one feature, noise level I have added. Don't worry about what I have done with the data, but just pay attention. So you can directly predict an alpha value, you can pass for ridge, and for Huber regression we have something called epsilon. Okay, for epsilon, as you can see, it's usually 1.35 only. Epsilon by default, okay, what Huber regression does is it optimizes the squared loss wherever it is below certain level epsilon. Epsilon is a value that you, by default it is taken as 1.35, but you can modify it if you don't get the good results, and you can also modify this alpha. Here alpha is a okay, it's still the strength of the L2 regularization. Okay, you can play around with this. Okay, with these values you can understand and implement, but for now, yeah, as you can see, slightly Huber regression has done better than ridge regression. So ridge regression is saying mean squared error is 426. Huber regression has decreased that by 6 points. Okay, slightly. And you can see that in difference in the line also. Green line is here, ridge regression. Huber regression has come up here. Ideally, if you see with human eyes, it could have done much better job by plotting in this direction. Do you agree? In this direction, stay as a diagonal line. If you are plotted like this, maybe the loss would have further decreased from 400 to 200 something. Okay, maybe that is where these other two regressors come in picture, Ransack and Thielsen, although I have not gone in depth on that, but I will take it up in the next class. So this completes the variations of regressors. Have you understood? Any doubts?
No
Yes,
doubts.
yes.